We'll look briefly at what happens when our frame of reference might be rotating. For example, the gravitron ride that we see, that's a rotating frame of reference. A space station that rotates in a uniform circular motion as well. What happens in those cases, and how do we analyze that motion? So, let's begin. Recall that in a non-inertial frame of reference, what occurs? We know that when we have a non-inertial frame of reference, Newton's second law does not apply, and therefore the observer will experience fictitious forces. Which we use to describe the motion in a non-uniform or in a uniform circular motion, but they don't actually really exist. When traveling in a rotating frame of reference, a centrifugal, there's an A in there, let me just respell this completely. A centrifugal force is experienced, which I will describe in 2 seconds what a centrifugal force does or what it looks like. Let us observe briefly in the Earth's frame of reference. And from our Earth's frame of reference, which is our inertial frame, what do we have occurring? Well, if it's a uniform circular motion, when we have an object, we know that we have centripetal motion, which is center-seeking, and that's our centripetal force and acceleration going towards the center of an object. So when rotating, if we have something like, let's say, the rail, string, wall, whatever is the outside of that circular motion, a centripetal force is center-seeking, keeping the object in a circular path. So that's why our object stays in that uniform circular motion, because of the centripetal force that's going towards the center. What if we look at a motion in the object's frame of reference? So in our non-inertial frame, where Newton's second law does not apply, our object undergoing a uniform circular motion yet again. However, in this case, we do have a force that is actually goes away from the center, and this is our centrifugal force. And our centrifugal force explains why our object resists the change in motion. And this is why if you're ever on a ride like the Gravitron ride, this is why we feel like we are being pushed outward. Now remember that our centrifugal force exists in a non-inertial frame to help explain the uniform circular motion. However, in our inertial frame where Newton's second law exists, this doesn't actually occur. So what happens if, say, for example, we are on a rotating space station that has a radius of 55 meters? How many times per minute does this space station need to rotate to produce a force that is about half of the Earth's gravity? So a rotating circular space station what occurs in this? Well, we know due to centripetal acceleration in our rotating that our acceleration is center-seeking. This is our centripetal acceleration that's going to move towards the center. And because our normal force is acting perpendicular to where our object is in contact with the surface, we know that this will be our normal force that's acting towards the center as well. So this tells us that our centripetal force in this case is actually merely equal to our net force, or normal force, which is mv squared all over our radius r. And we know that Fn in this case will be equal to half of Earth's gravity, so 0.5 mg will be mv squared, all divided by my radius r. M's cancel out on both sides. We're going to calculate for the speed in this case because the speed tells us how many times it will, or how long it will take for one rotation. So, if I'm solving for v like we did the other day, that will tell us that our speed will be equal to the square root of 0.5 multiplied by gr, which is merely 0.5 times 9.81 times my radius, in this case was 55, which is 16.425 meters per second. I do typically like to keep my calculations all in one color, but unfortunately my light green marker is running out. With our speed, we know that the period of one rotation, t, is equal to the distance it takes to travel around the circle all over our speed. Our distance is the circumference of a circle, so that would be 2 pi r all over v. Making these substitution tells us that 2 pi by 55.0 all over that speed of 16.425 tells us that it takes approximately 21.04 seconds for one rotation around this space station. But how many times per minute? So our frequency, which we know is 60 seconds per minute, we could take that 60 seconds and put it over the amount of time it takes to complete one rotation, 21.04 seconds. And what that tells us is that it takes about 2.85 revolutions per minute, so that we will have half of the Earth's gravity. So 2.85 revolutions per minute to produce this force. Really quite interesting mathematical analysis. There are no required problems for this course that I've given to my 4U students, but it is something that I felt that we should cover as well.